Hello everybody and welcome to this Copernicus Marine Service training. I'm Etienne Seug from Noveltis, and today I'm going to show you how to visualize some products over the Mediterranean Sea to visualize an upwelling event using some particular biogeochemical and model products. The Mediterranean Sea is an almost enclosed sea bordered by the European continent to the north and the African continent to the south. To the west, it is connected to the Atlantic Ocean by the narrow Strait of Gibraltar. The Mediterranean Sea represents less than 1% of the world's ocean surface, but it is one of the most busiest seas in the world. It carries 20% of the world shipping and welcomes more than 200 million passengers every year. This concentration of human activities has a great impact on its rich ecosystem. Indeed, the Mediterranean Sea is home to more than 10,000 marine species, 25% of them being native of this area. This fragile equilibrium is now threatened by the pollution, noise, fishing, and global warming, amongst other factors. Physical and biogeochemical events also occur regularly in the Mediterranean Sea, like upwellings. An upwelling is an oceanographic phenomenon that involves wind-driven motions of dense, cooler, and nutrient-rich water towards the sea surface, replacing the warmer and drained surface waters. The nutrient-rich upwelled water stimulates the growth and reproduction of primary producers, such as phytoplankton, and provide food for fish, marine mammals, and birds. Upwelling generates some of the world's most fertile ecosystem, as it is shown on this Earth observation from OLCI on the 22nd of November 2017. In this context, the operational, precise, and reliable Copernicus Marine Science products for the Mediterranean Sea are a great asset to analyze and forecast this kind of patterns. It is of great help to monitor and assess the biogeochemical state of precise regions suitable for fishing or aquaculture. So now we are going to use a GIS software to visualize observation and products model from the Copernicus Marine Service. To do so, we are going to use a plugin developed by Noveltis to use NetCDF data and treat and represent several variables from these NetCDF data. This plugin is called NetCDF2GIS plugin, and all the information to download and install this plugin are available on the user corner on the Mercator Ocean platform that you can find on the link with this video and the user manual of this training. So first of all, we are going to set our project settings, and then we will see how to open the NetCDF2GIS plugin. So you can open the QGIS software, and then you can create a new project. To this project, we are going to add a background, a map background. So to do so, you can just click on Layer, Add Layer, and go to Add WMS Layer here. Here we can connect to the map server demo, which provides several data of backgrounds for this project. So here you can click on Connect, and then you are going to choose the blue marble layer. You can add it to your main QGIS project. So here you have the background of your training exercise on your QGIS project. Now we are going to open the NetCDF2GIS plugin and see how to use it to display surface temperature variables from the Copernicus Marine Service data. So first of all, you can select this icon. So you just have to install the plugin following the user manual description, and then just launch the plugin clicking on this icon here. Here we can import several data which gather all the variables we need for our exercise. So click on the plus icon here, and then you can go to the directory containing your data. Here I'm going to import first of all the model product of the Mediterranean Sea, the physical model product reanalysis containing the temperature, which has a 4 km spatial resolution on a daily mean temporal basis. So I'm clicking on this product, click on open, and here if you click on your file and go to metadata, you have access to several information on this layer. So you have the resolution, and you have information from its origin and the name of the product you are visualizing. Here you have access to several variables. So now we are going to work with the theta O variable, which corresponds to the potential temperature. Now right click on this layer, and to display this variable for the month of November 2017, we are going to try to display the upwelling event, which is characterized by a cooling of the sea surface temperature. So we are going to sequence layers from the 18th to the 14th, the 24th of November. So select your first layer here, press Shift on your keyboard, select the layer corresponding to the 24th of November, and here you can click on Start. If you go to your QGIS project and zoom on the Mediterranean Sea, you can see that all the layers between the 18th of November and the 24th of November are scrolling one after the other on your project. So you have loaded kind of an animation of your temperature, of your surface temperature variable here. So when you're done with your animation, what you can do is just stop it and close this window. You can see that all your layers are still loaded on your QGIS project. So now we are going to just change the style of the one of these layers. To do so, you just have to click on the first layer, for example, and open the properties. Here we are going to set the minimum value to 13 degrees, the maximum value to 22 degrees. Just ensure to set the color ramp to spectral and invert it to have from blue color to red colors. Now you can click on apply and OK. Now if we deactivate the first layer, we can see that the color scale has not been changed for the other layers, so we are going to copy this style to the other layers. To do so, right click on the first layer you have set, go to style and select copy style, and now select the following layers and right click on it and paste style. Now you have the same value range for all your layers, and you can compare them. So if you just activate the layer corresponding to the temperature of the 18th of November to the one corresponding to the 24th of November, you can see that the surface waters are cooling here all along the western coast of the Adriatic Sea, along the Italian coast here. Again, so you can see the difference. Now we are going to do some computation, and we are going to highlight the extent of sea which is under a certain temperature threshold. As you can see here, the extent of water in blue, so cold waters, is higher than here. So we are going to convert all these layers to polygons and compute extents of waters under a certain threshold. To do so, we are first of all going to convert these two layers to polygon layers. We have raster layers here from NetCDF, and we are going to convert them to polygon layers. To do so, you can click on raster, conversion, and polygonize here. So first we are going to polygonize the layer corresponding to the 18th of November, create the field temperature, temp, and just we are going to save the resulting vector layer to file. So here we can call it 18th of November 2017 at midday underscore temp dot shapefile. Then you can save this layer. So here I'm just overwriting an existing file. Now you can click on run and close. So here you can see that all the layers have been converted to a vector layer, and then we will see how to filter temperature higher than 0 degrees and under 14 degrees, which will be our threshold. So I will just polygonize my second layer corresponding to the end of the upwelling event. So again, click on raster, conversion, polygonize. Here we have the theta O layer corresponding to the 24th of November. We are creating the temperature field, and we are going to save this file again. Overwriting it. Okay. Now you can click on run. Close. We are going to select these two vector layers here by pressing Ctrl on your keyboard and just drag them out of the sequence group here. So now we can apply a filter on these polygon layers to only keep the polygon corresponding to this area here in blue under a certain threshold. So we will set a threshold to 14 degrees Celsius, and we are going to apply a filter. So go to your first polygon layer here, right click on it and click on filter here. So we are going to apply a filter on temperature. So we want temperatures higher than 0 and lower than 14 degrees, lower or equal to 14 degrees. Then you can click on OK. So you can see that if we deactivate this layer, we can see that this polygon in pink corresponds to the cold surface waters on the 18th of November and corresponding to the raster layer here. And there are some other places where the water was cooler than 14 degrees here. Now we can apply the same filter to the layer corresponding to the 24th of November, the polygon 1. Right click on it and select filter. Here we are going to apply the same filter, higher than 0 and lower than 14. Click on OK. So now you have your two polygon layers of temperature, of surface temperature, filtered under a threshold of 14 degrees. Now, before anything else and before any other operation between polygons, we need to fix these geometries, because as you can see there are several polygons in one layer, here and here. So we need to fix all these polygons before computing any other operation. To do so, I invite you to click on processing and open a toolbox, the processing toolbox here. And here you can just type fix to open the function fix geometries. Okay. Now we are going to select first of all the vector layer corresponding to the 18th of November 2017, where the temperature is lower than 14 degrees. Select this layer as an input, and we are going to set the fixed geometry to another file, to the same file name, but we had an underscore F for fixed geometries at the end. Now you can click on run and put this geometry on top of the first one. And we are going to do the same with the 24th of November geometry. And again, save to file and add the underscore F extension. Then click on run. Okay, so now we have our two geometries where temperature is under 14 degrees, but with fixed geometries. So we can do some intersection or any other action between our vector layers. So what we want to do is to compute the total area where the surface temperature is under 14 degrees for these two dates, the 18th and the 24th of November. And we just want to compute the area on the Italian coast here, and not take into account this this part of the polygon. So to do so, we need to extract these polygon layers onto a polygon along the Adriatic Sea Italian coast. So we are going to create this polygon. To do so, just click on layer and create layer, and we are going to create a new shapefile layer. We are going to call it, sorry, just browse the directory you want to create the layer, and we are going to call it Italian coast. We are going to set the geometry type to polygon, and we can click on OK. So the projection is a classic one with longitude and latitude data, 4326. Click on OK. So the layer is already existing on my computer, so I just I'm just going to overwrite it again. So drag this layer on top of all the others, and now we need to draw our polygon on this layer. So to do that, you need to toggle to editing mode by clicking on the pen icon here, and now you can click on add polygon feature here with the polygon icon. Now we are just going to draw our polygon here along the Italian coast, and we are just going to select the northern part of the Adriatic Sea. Okay, so here we are following our polygons, and we are good. So once it is done, right click on your polygon and select an ID for this polygon, as you can set several polygons in one shapefile. Click on OK, and now just close the editing mode by clicking again on this icon and save the changes added to your Italian coast shapefile. Click on save. So now we have this polygon on the Italian coast. What we are going to do now is to extract this polygon here, so corresponding to the surface temperature under the 14 degrees threshold, but with other polygons here, to these limits of the Italian coast polygon. To do so, we are just going to compute an intersection between our Italian coast polygon and this vector layer with fixed geometries. So we need to select Vector, Geoprocessing Tools, and here we are going to open the intersection function. So the input layer is the Italian coast polygon, here, the yellow one, and the overlay layer, is the 18th of November 2017 temp_fixed layer. Now we can just set the intersection layer resulting from this operation and save it to file, and we are going to call it here the 18th of November temperature layer on the Italian coast .shapefile. Now you can click on run and close. So here, if you compare your layer here in brown extracted on the Italian coast and the one not extracted, you can see that here we have only kept the polygons which are located on the northern part of the Adriatic Sea. We are going to do the same with this layer corresponding to the 24th of November. So again, Vector, Geoprocessing Tools, Intersection, and here we are going to select the Italian coast as input layer, the 24th of November 2017 as overlay layer, and just set the resulting intersection layer. Now you can click on run and close this window. So if we put the two extracted layers on top and deactivate the others, even the Italian coast, we can see that they are both only located on the Italian coast here. And now there is just one last step before just one last step before computing the area covered by each of these polygon layers. So what we need to do now, as you can see, if you select the identify feature option and select one of the two layers, there are several polygons in one layer, one corresponding to the temperature of 14 degrees, the other part to the 13 degrees polygon, and so on. So what we need to do now is to just merge all these polygons of different temperatures before computing the total area. So to do that, we are going to select again Vector, Geoprocessing Tools, and select the Dissolve here function, which allows us to compute one single polygon. So what we are going to do is to just select this layer here as an input layer, the one extracted on the Italian coast, and we can select the output name of the resulting layer and save it to file with the merged extension here. Once it is done, you can click on Run and close this window. So here you can see that you have merged all the different polygons of this layer to create the resulting one. Oops. We are going to do the same with the layer corresponding to the 24th of November 2017. Vector, Geoprocessing Tools, Dissolve. Here I'm selecting the layer of the 24th of November on the Italian coast and just saving it to file with the extension merged. Now you can click on Run and close. So I drag this new layer on top. So now the last part of, as we can see, first of all, we can see that the extent of waters with surface temperature below the 14 degrees threshold is higher after the upwelling event, here in brown, in comparison with the extent of waters below the threshold before the upwelling event, in gray. So we are just going to compute the extent in squared kilometers for each layer. So to do so, I'm just going to select the first layer, right click on it and open the attribute table here. And now I'm just going to compute a new attribute for this polygon layer. So here you have access to the open field calculator. Click on it. So first of all, open the editing mode here. Click on the field calculator. We are going to set the new column to area in squared kilometers, and here just type the expression multiplying the area of this polygon layer by 10 exponent minus 6. So now you can click on OK, and you can see that the area in squared kilometers where surface temperature is under the 14 degrees threshold is 3,207 squared kilometers. Now let's compute the same thing for the layer of the 24th of November to compare the extent. First of all, close the toggle editing mode, the editing mode here, and save the area in squared kilometers to this layer here, and open the attribute table of the second layer. Open the editing mode, click on Fill Calculator here, and we are going to do the same. Create this new field and compute it with area multiplied by 10 exponent minus 6. Click on OK and close the editing mode. Save the modifications brought to this layer, and we can see that now the area in squared kilometers is 3 times higher. So after the upwelling event on the 24th of November, in comparison with the 300 kilometers we had obtained just before for this layer. So we have seen how to use physical model reanalysis data on the Mediterranean Sea from the Copernicus Marine Service to highlight the cooling of surface waters that occurred during an upwelling event in November 2017. Now, the next step of this training is to try to visualize observation wind fields to see if there are some parallel winds directed northward that can have led to this upwelling event. To do so, we go back. We can close the two attribute tables here. We come back to our plugin. Here we are going to load the data, the netEDF file containing observation data at the L4 level from the Copernicus Marine Service. So these data are from the CERSAT platform. Click on Open, and here, if you go to metadata, you have information on the resolution. These data have a 25 kilometers spatial resolution and are distributed with a 6-hourly mean temporal resolution. We have downloaded this data from the 15th to the 25th of November 2017. We are now going to see how to display a vector field using this netCDF to GIS plugin. So to do so, it's really simple. You first have to import to your project the two scalar components of your vector field, so eastward wind and northward wind variables, and then compute a vector field time step by time step. So I'm going to import the eastward wind component of my vector field. Click on Add Layers this time to simply import one layer, and I'm going to import my wind layers from the 18th at noon until the 20th at midnight. I can select all my layers by pressing the first one, pressing Shift on my keyboard and selecting the last one, or I can use the Control key on my keyboard. So here I just click on Add and Close. So all these layers have been added to my project, and I'm going to do the same with the northward wind components. Click on Add Layers, and we are going to select the same time frames. So from the 18th at noon until the 20th at midnight. Again, Add and Close. So here, as we can see on the background and here on this layer tab, we have added to our project each component eastward and northward for several dates. To draw our vector field, we need now to combine these two components, and there is a special function on our NetCDF2GIS plugin to compute these vector fields. So select for the same date the two components, right click on them and select vectorize. So here we are using UV components. We are using a norm or a projection of wind and wave. You have also the current choice, but we are keeping wind and wave, and we are not applying any downsampling, which correspond to a factor to reduce the number of errors of our vector field. Just select an output directory, for example here, and just name your vector field. Here we are going to type the dates, so 18th of November 2017, and the hour corresponding. Once it is done, you can click on vectorize, and you can see that the vector field have been computed in the background here. To see it better, you can just zoom on the region you are interested in, and you can deactivate the northward wind and eastward wind scalar layers, because we only want to see our vector field. So just deactivate the temperature field also. So here you have your vector field over the Mediterranean Sea and the Adriatic Sea in particular. Now we are going to do the same thing for each time step between the 18th of November to the 20th of November, every 6 hours. So close this first window, select the following time frames corresponding to the 6 p.m. and again select vectorize and rename the resulting layer. So I will do that for all the layers. It takes some time to compute every layer, but just do it slowly. And then we will see how to tune the style and compare several vector fields. Nineteenth of November at noon. And let's do this for the two last times frames we want to display. Be careful to select the good time frames for each component. And the last one, eastward and northward. Vectorize and just rename the last vector field. For the 20th of November at midnight. Click on vectorize. Now you can close this window and reduce the NetCDF2GIS plugin. So what we can do now is that we don't have the same vector values and ranges for each time step. So what we need to do is just to apply the same style for all these vector fields, and then we will compare them. So you can just reduce here the size of each time frame. For example, just let this one open, and here we are going to change the style of this first vector field. If we deactivate all the others, right click on the first vector field and open the properties. So now you are on the properties, just go to symbology here, and here you have access to this button style, and you can load a style from some files. So we have provided a style file already edited by Noveltis for this exercise, so we are going to load this style file for each wind field. So browse to your directories, and the style file is named wind field style. So this file will be provided on the user corner on the Padlet of the Copernicus Marine Service training material. Open this style file, and once it is done you can click on load style. So here you can see that the values have changed and the ranges also, and now you can click on apply and click on OK. So now we have a style, a particular style for this vector field. We are going to apply the same style to all the other layers. To do so, right click on this first layer, go to style and copy style. Here we can just copy the symbology style. Select all your other layers, wind vector layers, pressing shift on your keyboard. Right click on it and just paste style here. So now if you compare, you have the same categories of vector classes between all your layers. So now we can just activate and deactivate each layer and see how the wind vector field has evolved during the few days before the upwelling event. So let's see it. So we, on the 18th of November at midday, the wind was along the coast here and turning east on the north of the Adriatic Sea. Then it was just north and following the coast here. Again on the 19th at midnight. At 6 a.m. on the 19th, the wind was directed mostly westward. It was the same on the 19th at noon, and then it was also going northward on the 19th at 6 p.m. and turning to the east at midnight. So what we can see is that the wind was always directed northward during the period between the upwelling events, and it enables the moving of surface waters to the north, and it involves Neckman pumping, which provoke the upwelling event with the consequences we know, a cooling of the surface waters, what we have just seen before. And now we will see the impact on the chlorophyll A concentration on surface waters on this last step of the training. So what we can do now is just hide the vector layers, and we will now work with the chlorophyll A concentration between the 18th and the 25th of November 2017. So the upwelling event produces pumping of deep waters to the surface, and it brings nutrients to the top of the water column, and there are chlorophyll blooms after. So we will use Mediterranean Sea biogeochemical reanalysis on the month of November 2017 to display this chlorophyll A bloom. So go to the NetCDF2GIS plugin again and open the reanalysis of the biogeochemical model from the Copernicus Marine Service with a spatial resolution of 4 kilometers, as we can see on the resolution panel here on metadata, and with a daily mean temporal resolution. So here we are focusing on the chlorophyll A concentration in seawater, this variable, and we will see its evolution daily. So right click on this variable, select add layers, and we are going to select layers from the 18th at midday to the 25th at midday. We are here selecting, as we have several depths, we are going to select the one which is the closest to the surface, and then you can click on add and close to add these layers to your project. Quickly, if we just go from one layer to the other, we can see an evolution of the chlorophyll concentration. But first of all, we are going to change the style of these layers to highlight high concentrations. So here on the first layer, open the properties, set the minimum value to 0 and the maximum value to 2 milligram per cubic meters. And here, just be careful and invert the color ramp to have blue values corresponding to low concentration and red values corresponding to high concentration rate. Apply and OK. Now you can just copy this style and apply it to the other layers, and you can just see how it evolves a long time. So here these 2 days are before the chlorophyll bloom, and then starting on the 20th of November, and it is clearly seen on the 21st of November there is a chlorophyll bloom, which is then reducing after the 23rd of November. So the maximum chlorophyll A concentrations are found on the 21st of November 2017. Now what we are going to do is to extract this chlorophyll concentration to the polygon we have first developed on the first part of this training, the Italian coast polygon. And then we will compute some statistics over the chlorophyll concentration over this region to see the evolution of the chlorophyll concentration after and during the upwelling event. So first of all, we want to extract some raster layer on shapefile polygon. So we need the raster extraction and clip raster by mask layer function here. The input layer will be the chlorophyll 18th of November layer, and the mask layer will be the Italian coast layer. We are just going to keep the resolution of input raster here, and just select and save to file the resulting layer, which is the extraction of the chlorophyll concentration on the Italian coast polygon. So we are going to save it here as a TIFF, and we will call it 18th of November 2017 chlorophyll on Italian coast polygon. Then you can click on run and close. So this resulting raster layer can be put on top, and you can see that it's the extraction of the chlorophyll layer only on the northern part of the Adriatic Sea along the Italian coast. Let's do the same thing for the 21st of November during the upwelling event. Again, raster extraction, clip raster by mask layer. So the input layer is the chlorophyll of the 21st of November, and the mask layer is the Italian coast. Keep the resolution of the input layer, and here we are just going to save to file the resulting clipped layer. Just change the date, so here we are on the 21st of November. Click on save, and then you can click on run and close. So drag this new layer on top of the first one. Okay. So now you can just deactivate this Italian coast polygon and just deactivate the chlorophyll original concentration layers. We are just going to copy the style of these layers to apply it on this one, which are on the gray level. So select both of the extracted layers and paste style. Okay, so now you can see that there is a clear bloom of chlorophyll on the 21st of November 2017 here. And what we can do is to apply some statistics only on this polygon on the Italian coast of the northern Adriatic Sea to see, for example, the mean concentration of chlorophyll onto this polygon. So to compute these statistics, we again need to open the processing toolbox here, and here we are going to search for the zonal statistics function, this one. So our input layer is is the chlorophyll. No, I don't need this function. So just click on the raster layer zonal statistic here, and we are going to apply statistics on this extraction of the chlorophyll on the Italian coast polygon. So now click on run, and then you can click on close, and here you have several statistics of this 18th of November polygon layer, sorry, that have been computed. If you double click on this statistic here, you have so now we are going to compute statistics of the chlorophyll concentration layers on the 18th of November and on the 21st of November on this Italian coast polygon. So on the area represented by this layer extracted before. But we are going to compute this statistics on the complete chlorophyll layer of the 21st, for example, but we will set the Italian coast polygon as a polygon of computation. So what we can do is just open the zonal statistic function here, select as an input layer the Italian coast polygon, and select the chlorophyll on the 18th, not extracted already on the Italian polygon here. Now what we can do is to select the statistics to calculate, so click on the dots here, and we are going to select the mean, the variance, and the minimum and maximum values. Click on OK. So we are 4 options to compute here, and just save the file of the resulting statistics layer here, stats, with the date of the 18th of November and chlorophyll with the shapefile format. Now you can click on run. Now do the same with the layer of chlorophyll, the whole layer all over the Mediterranean Sea for the 21st of November. So select here the Italian coast polygon, the raster layer corresponding to the 21st of November, all chlorophyll concentration all over the Mediterranean Sea, and the statistics will be computed only on the Italian coast corresponding to the extent of this layer here. Again, select the statistics to compute, so we are going to select mean, minimum, maximum, and variance. Click on OK, and here we are going to set the name of the output layer with stats 21st of November 2017 and the variable chlorophyll. Click on save, and then you can run this computation. So here we have selected and computed statistics over this Italian coast polygon with chlorophyll concentration layers all over the Mediterranean Sea, and we can compare the values of these two layers, and we will see that the chlorophyll concentration has evolved between and during the upwelling event. So if we open the attribute table of the 21st layer and then open the attribute table on the 18th layer and put together the two statistics, we can see that on the 18th the mean concentration of chlorophyll was 0.3 milligram per cubic meters, and it has been almost doubled during the chlorophyll bloom with a 0.6 almost concentration. So the minimum and the minimum concentration all over the Italian coast polygon is the same, but the maximum concentration is very higher during the bloom event, which is logical. And what we can see is that the variance is very higher on during the upwelling event, as the maximum values are higher than the mean values during the chlorophyll bloom event. So we have seen during this training how to see the cooling of surface waters using the Copernicus Marine Service model products, which is a testimony of an upwelling event coming. We have seen how to visualize vector fields as winds, which can be at the origin of these upwelling events. And we have seen how to display chlorophyll bloom and compute some statistics to see that there is an upwelling of nutrient-rich waters after parallel winds to the coast. So that was the definition of an upwelling event on the end of the month of November in 2017. So now it's time to you to download other data on other region and to see if you can spot any other upwelling events. Thank you for your attention and see you. Bye.